First thing I want to address is the exam, which is not next Wednesday, but next Wednesday, to quote somebody else. So keep that in mind. Most of the first exam, or a significant portion of it, is kind of based on review content. So you should be starting to take a look at that. So general strategies for exams. You've got the practice ones available. I forgot about the 235 ones, so those just went up 2 minutes ago. So if you wanted to look at the first semester exams, you can go through and do that. These are literally just what you would get for the exam. So that's what I'm showing you and giving you access to. Okay? Good idea to go through and read the directions just to get a feel for what I'm asking of you and potentially what things might be useful for you. I do give you a periodic table. Hopefully we don't get the line mismatch there. I'll try and fix that for future. You get short answer questions. Okay? Notice with these you're starting to get some questions about HOMO and LUMO. This is really chapter 14, which we've kind of just left alone for the moment, and I'm expecting you to kind of read through it and review some of that content. It is looking at a diels-alder reaction, so we could go through and try and process through that. A lot of students will jump immediately to the short answer because they tend to be worth more than an individual multiple choice. Okay? General rule of thumb, stop doing that. Okay? A short answer may be worth more points, but if you don't know it, you're wasting your time. Regardless of how many points it's worth, you don't know it, you're going to get it wrong. Okay, so what you should be doing is skipping through the exam to find questions that you do know the answer to. Answer those first while your mind is fresh and clear. Then you can double back to those questions you were going to get wrong anyway and try and do something with them. Okay, makes sense? So multiple different styles of tests. Me as a test taker, it's provide everything and then give you the opportunity to show me what you know. Okay? If you go through it in sequence, you aren't showing me what you know. What you're doing is how other tests are built, which is just put all the information in sequence of the test on the test. Right? A test is supposed to get at everything, and ultimately what they're trying to find is not what you know, but what you don't know. So if you can write down first what you know, it's a more accurate representation and a better representation of what your grade should be. Right? So don't start immediately with the first question or even the second. Go through and find something that you do know. Right? For those of you that haven't had me, I do tend to throw in what I would call Easter eggs every so often. So read through the practice tests and you'll get a feel for what some of those Easter eggs might be. One of the things that I count as an Easter egg that most people wouldn't is that some of the short answer can help you answer multiple choice questions. Right? And vice versa. You could use some of the multiple choice to help you answer a short answer. Okay? Believe it or not, they are there. Okay? During a high stress environment of the test, you may not recognize those patterns. If you go back through, you can actually usually find them if you dig hard enough. Okay? You do get extra credit every so often, so watch out for those. Again, if you know the answer, write it. Otherwise, don't. Big change from first semester. Every test is going to have some mechanism type question on it. Okay? So you have to know your mechanisms. Reagent predictions for synthesis, whatever you want to call them, okay, which we will talk about sort of in chapter 13. It's really just a list of approaches to how you would solve that question. This I would call an Easter egg. Okay? It's providing definitions. Okay? When I first started teaching OChem, I had students going through second semester that couldn't tell me what a nucleophile was. Okay? And so it became so frustrating that at the end, like one of the last tests, it became a subtraction of points. If you can't tell me what a nucleophile is, I'm subtracting points from your exam, which means you could end up with a negative score on the exam. Okay? So early and often, you'll see these definition kind of questions come in to varying ways. It's not always just what is the definition. A lot of it is going to be more application. How would I apply that definition to a comparison between those pieces? Okay? And then we'd run into the multiple choice. Okay? And the multiple choice, varying styles, just deciding what the reaction is, predicting reactants, predicting products, okay? Looking at molecular orbitals. So you get kind of a big mix of different things. Most of second semester is predicting reactants and products. There really isn't any way around it, or reagents. That's what we see a lot of. You'll notice in some cases, for instance, with whatever this question is, question 5, we don't see any stereochemistry popping up, but stereochemistry pops up in question 8. Okay? So you may not always be asked about it, but you're responsible for it all the way through. Okay? Strategies for preparing for the exam. Okay? I'm telling you, you should be looking at this now. Go through it. Take it right now, after class. Okay? And answer every question that you think you know the answer to. Okay? Find those and do it as quickly as you can, kind of test taking pressure, 75 minutes. Okay? And answer every question that you think you should know the answer to. Okay? Skip any question that you don't think you should know the answer to, because you don't know the answer. Okay? You've then covered the baseline for the exam. Go back through it after that and look at questions where you didn't know the content and see if it's something that maybe you should have known. Okay? Start to match it back to the lecture, match it back to the textbook, and see if you can figure out the answer to those questions. Once you've got all of the answers, or for that matter, if you've only done part of it, you can email me. Email me your answers and I'll give you feedback. Okay? I will also ask, is it okay for me to post these answers to the discussion board for everybody else to have access to? Okay? I will remove your name from it, okay? But what you will see will then be my comments and all the student answers. Make sense? Okay. The other reason so I think that works for preparing for the exam in 2 weeks. Okay? That means we've got 4 lectures left. Okay? I would like to get as much covered within those 4 lectures as possible, but at the same time, get some practice behind this. You were supposed to watch the diels-alder video. Question 11 is a diels-alder question. Okay? Why might we go ahead and draw attention to this one? So one, you've watched the diels-alder video. As you see this multiple choice, does it jump out at you as a diels-alder question? Okay. You're saying no, why not?
Because like typically from the ones we're used to, we just see like a half degree sort of thing. You know?
Okay. So a couple arguments for why I would argue this doesn't look like a diels-alder question. Do I say diels or alder? No. Okay. I care less about the name than about the chemistry. Okay. If we look at the classic diels-alder reaction, it's something along these lines. Are the reactants drawn in that format? No. Okay, so that makes it further misleading. Okay, so one of the things that you might need to do is start to look for patterns and recognize what you see within it. Okay, if we look at just the answer choices, you might start to see a pattern because our diels-alder reactions usually result in a cyclohexene structure, and we have 3 of our answers with cyclohexenes. Notice one of them is not. Why?
Confuse you?
It's ultimately there to confuse you. Remember, we're not in the diels-alder format. It's not inherently obvious that you're going to be doing a diels-alder reaction. Okay? So that's why that answer choice is dropped in there. Kind of makes sense? All right? Once we know it is a diels-alder reaction, we now have to go through and predict the product, which you should theoretically be able to do. But since there's a question,
So how did you know it was a diels-alder?
right? How do we know it's a diels-alder is looking potentially at our structures here, saying 3 cyclohexenes. More than likely, that's going to be our red flag that we're looking at a cyclohexene formation. If I have a cyclohexene, it's now going back and looking at the starting materials and see, do I match that pattern? Okay? And yes, in this case, I do. It's just oriented very oddly. Okay? There's my dienophile, which I'm just going to write as file. Whoops, screwed that one up. This is why I don't like memorizing names. That would be our diene, and this would be our dienophile. Okay? And if we go back through, yes, that structure matches. It's just in the S-trans conformation, and it needs to be in the S-cis. So we'd have to get it converted into the S-trans. Okay? In the process of doing that, I could rotate about the sigma bond, and I would end up with a structure looking along these lines. Do I have to stress about that methyl group in this case? Right. Those of you asking, well, what do you mean? Right. If that methyl group had instead been written here, everybody see the purple? Would I now have to stress about it when I went over to the S-cis?
Yeah, because then it'd be inside.
I have to make sure that that methyl group, or that alkene in particular, maintains the proper arrangement, be it cis or trans, when it moves over to the S-cis conformation. And as Cass is pointing out, she thinks that that should be, you said pointing inside. Okay? I have a hard time with seeing that. Does anybody else have a hard time seeing that that purple one should be aimed inside? Seriously? Nobody has a problem? You have a problem with it? Thank you. Okay. Okay. We look at that double bond. God, I'm like the only one that's an idiot? That's not fair. I mean, that did not come out right. I apologize. If we take a look at the double bond, right, we split it in half. We're looking at hydrogen versus carbon, which is higher priority? Carbon. We go to the other half, it's carbon versus carbon. No difference, so I go one atom further away. Carbon versus hydrogen. Star. The purple double bond needs to be what configuration? Cis. So when I go through to draw that purple methyl group on there, I have to make sure that that double bond is in an S-cis configuration, or sorry, cis configuration, which means it has to be aimed inwards. So Cass, being awesome with her three-dimensional rotation stuff, recognized correctly that it was cis. Okay, and it needs to be aimed inside. Okay? If you're good with the three-dimensional rotations, by all means, you can just jump to it. One of the problems I have with that is it is either cis or trans. It's either inside or outside, which is really a 50-50 split. Okay? What I've noticed is that it tends to be a coin toss which way it goes. Maybe you're right for the wrong reason. Okay? If you're saying, well, that's not that big a deal, remember, there's our first flip, 50%. What happens when we react with our alkene, our dienophile? We would have to draw on our dienophile. Is it oriented this way? Or is it oriented this way? There's two ways it could have reacted, right? Which is another 50-50 split. You put just those two 50-50 splits in there, if you're getting it right for the wrong reason, the odds of you getting the question right just drop to 25%. No better than just guessing right out of the gate. Okay? This is why OChem becomes very dangerous. When you go through and solve questions, you need to make sure that you're getting it right for the right reason, not right because you lucked into the answer. Each of those easy questions can be a 50-50. If I string three 50-50 questions together, if you're guessing at each of those 50-50s, it was better to not even read the question and just outright guess. Okay? I don't know about you, but if you get only 25% right, I'm not going to be happy. Okay? So I want to make sure you understand why it's right in each of those cases. Does that make sense? Okay. Because that unnecessarily makes this question more difficult, I'm going to erase all that. So we have our diene, and then we have our dienophile. Note, we simplified it by removing that extra methyl, because it's not there. Okay? Now we have to bring in the dienophile. The dienophile is still going to bring in the same issue that we presented earlier. The orientation can either come in that way, or it can come in this way. Does that change the product? If you aren't sure, what should you do? Draw it. If we go through to draw this out, attacks, 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 and now I'm going to erase all those arrows. And the resulting structure, double bond, a methyl group. Yes? If we did it with the green one, attacks, attacks, shifts, again, let's clean up the arrows. Everybody agree? Are those structures the same? No. Okay. So what does that mean? It doesn't mean we should be pounding on the walls.
We should figure out which one's more stable.
We need to know which one's correct. Okay, we could try and do an evaluation of which one's more stable. That becomes tricky. What are you referencing when you're saying which one's more stable?
Total energy and all the bonds
Of what?
of the sigma and pi bonds, of the carbon to carbon, the carbon to oxygen,
In what?
in each of the products.
Okay, so we want to evaluate the energy of the products. That, unfortunately, isn't going to help us out for a number of reasons. The first reason being, are any of the sigma and pi bonds actually different? No. Okay. Next reason I would add to that, what is the bond energy of a carbon-carbon sigma bond? Silence is not a good answer. Okay, I don't know what it is either. Okay, if you don't even know what one bond is, how are you going to be able to figure them all out, even if there was a difference there? Okay, so that becomes challenging. Okay. The next part is, if we're evaluating it at the product, we're already past the stage that's important. When we look at a diels-alder reaction, the product is dictated based on the kinetic product. Okay, so we could jump to intermediates. There is no intermediate in the diels-alder. How do we see a difference between our products? The transition state, okay, dropping. Okay? And that really only tells us between endo and exo. Are either of these being specified as endo or exo? No. So that also doesn't help us out. Okay? When we look at the diels-alder reaction, one of the things that tends to kind of disappear from it is charge. And we might say, well, why might charge disappear from our interpretation of the diels-alder reaction? It's a really stupid, obvious answer. There is no charge. Okay? Maybe if we drew charge, that would help us interpret how the reaction is going to work. Okay? Let's start with the dienophile. How could I get charge drawn into either of those dienophiles? Okay, we've got the carbonyl. Oxygen's the most electronegative element, right? At least within this problem. That pi bond's probably going to shift up to the oxygen. Is that pi bond doing the chemical reaction? No. So while that is a good resonance arrow, I can't stop there. What do I have to consider? How the other pi bond is affected. Should mean it would shift here, yeah? What would the resulting resonance structure look like? Okay. So we already have a doubter. That doesn't really help.
If you do the same thing to the opposite one, you get the positive charge.
If we look at the other dienophile orientation, we get the exact same resonance. I completely agree. What have we not looked at? The diene. Okay. And when we look at the diene, you might say, well, there is no electronegative element to cause a shift in electron density. Okay. And you're absolutely correct. However, this structure is going to react slightly differently than if that was a hydrogen. What is the difference between hydrogen and what is that atom? What is at that red point? A CH3. So what is the difference between a hydrogen and a carbon? Carbon has more electrons. Okay? If it has more electrons, what could it sort of kind of do with that? it could share those electrons in. And for those of you being, that is ludicrous, you're pretty much right. Why would you say that is ludicrous? That's a good response. Okay, it would break the octet, and it actually breaks 2 octets, right? Because that was a methyl group out there. Okay, if it broke the octet there, where would the electrons in our second pi bond go? To the outside. So really, what we're saying is that this happens. Yes, we have a big issue of breaking the octet out there, and yes, we can scream and yell about that all day. But this isn't a question of saying, is this the right structure or a correct structure? What we're saying is if that was carbon instead of hydrogen, this is a possible-ish structure. Okay. Why is that helpful for me? If the negative charge builds at that position, what does it need to react with? It needs to react with the positive charge. Now when we go back to our dienophile, where's the positive charge? Which of those orientations is going to better match? Top one, which then means the red structure is my better product than the green structure. Resonance, even when it's a bad resonance, and really what we're trying to show here is not resonance on the diene. What we're trying to show is an inductive effect, a pseudo-reverse inductive effect. Carbon has more electrons can donate into that structure, building a negative charge at the bottom carbon, which then means when I go through to run the reaction, I want the positive carbon of my dienophile to align with it. The green one does not show the proper alignment. The red one would. Which means the green one is not the likely product. The red one becomes the likely product. Okay, so we at least have a hand. So one option is to go through, well, the 2 largest groups are as far away from each other as possible, and unfortunately does not always work. Okay, I'm pretty sure it's in SmartWork, right? Because you had a question about this. SmartWork has a question where they actually are on the same side. Okay, so we can't use a steric effect. So when we think about how reactions work, we should look at electronic effects before we look at steric effects. Our electronics are always the charge. Really, resonance is the first thing that's going to set you up with where that charge is found.
So we only have like 40 seconds per question. So
Yes.
what's the real way to solve this? I'm just being practical.
No, and I understand.
Because when I originally looked at this,
How long
my
should it
answer
take you
would be,
to do a resonant structure? Those resonant structures should be drawn, if you're going to draw them, in under 5 seconds. Okay. Which I spent a long time going through and drawing out and talking through. Why? How many of you are comfortable with resonance? Okay. Not so many. Resonance becomes the driving force for virtually everything we do this semester. You need to start drawing resonance quickly. Every time you start a question, it should be immediately drawing out the resonance structure, okay, and using that information to help you answer the question, particularly as it pertains to how a reaction is going to occur. Okay? I would also make the argument that by the end of this semester, probably exam 3, verging on the final, you shouldn't have to draw the resonance structure to establish where the charges are. Okay? Instead, what you should be drawing, yeah, I'll just erase some more space. I don't really have a lot of space. Well, I'm just going to clear it all. What you should be drawing when you see this question is immediately drawing the resonance contributors. So it's not a question of redrawing the structure. I'm immediately jumping to the resonance contributor. I'm not adding arrows. I'm jumping immediately to it and now saying, how do those pieces align? Right? That cuts out steps and time. Yes?
Can you explain just one more time why the red was more, like why was the positive charge on the red group more likely to connect with the negative diene than the other one? Like why?
When we run this reaction, let's show it in green. We're going to take the pi bond and share across to that carbon, right? And then, of course, I aligned those charges wrong. And then share, and then share. That's our overlay for our diels-alder reaction. Yeah? Okay. If we were to go through and do that, the electrons from one need to react with the carbon of the other. Okay? So the charge here had better be what with the charge on the other side? Opposite charge. So negative to positive. If we flip it the other direction and had the orientation set up this way, there's my positive. And you might say, well, don't those interact? Yes. Can this carbon now interact with that carbon? No. It's now distance-wise aligned the wrong direction. It would have to do a full rotation up to get there. Okay? Which would then mean it's not a concerted mechanism, which it is. Does that make sense? Okay, so it's all about that proximity. Okay, so we do have a lot of valid points behind this. There's a time crunch behind it. We have to look at the question, quickly identify its diels-alder, quickly identify what those resonance contributors are, and then mash the structures together. Okay? If you don't know anything, we don't know its diels-alder, what could we start to do then? Well, 3 structures have rings. More than likely, my answer has a ring. Now look, what's the difference between those 3 answers? It's not just a position. We have an oxygen in the ring. Would I expect the oxygen to be willing to react with the carbon? Probably not. That one's gone. I'm now looking at A versus B. What's the difference between A and B? Where the methyl group is, and I'd be careful with that, in relation to the other substituent. Okay? Because if we look at answer choice B, it sure looks like, depending on how we drew it, okay, our methyl group has changed locations. The methyl group didn't change locations. What happened? We picked the whole structure up and flipped it over. If we go through and draw out the product as we would have anticipated it, our double bond. Exactly as we drew it, right? Lined up perfectly? That looks like B, doesn't it? Methyl's lower left-hand corner, I got the double bond, there's my ring. Answer's B.
Is it A?
It's not B.
Yeah.
Because I also have to acknowledge where the carbonyl is. Okay? The standard format for our diels-alder is aligned nice and beautifully here. Why did we pick the standard format for drawing the diels-alder? Because it's a mother effing hard question. It requires tons of spatial awareness to put all those pieces together, so we're going to lock into a standard pattern. As soon as we've locked into a standard pattern, we then start to lose focus of the chemistry, and we guess the wrong answer. Why is that answer choice placed there? It's taking advantage of, and you could blame me, and it is partially me, but the ACS is aware of students just trying to memorize the pattern. So what did they do? Just a simple tweak to the structure by flipping it over that now breaks the pattern. That answer now looks incorrect for all of the wrong reasons. This is why you have to know what's happening in each of those stages. Okay? I would argue the diels-alder question is insanely difficult because there's so many different layers to it, which is why on a test I would skip it. Okay? There's too many pieces falling along behind it. Okay? Kinda? Okay. Last thing I want to address with the diels-alder, what is wrong with answer choice A? So, wait, don't answer that. Okay. Do we all acknowledge that answer choice A is the best answer? Okay. What is wrong with answer choice A? Where that carbonyl is attached, is that a stereocenter? Yes. Okay. So how could this question be made even more difficult? We could throw in wedges and dashes. Okay. Add to this, okay, it says predict the product of the reaction shown. That isn't saying the only product. I could go through and show this as a wedge and then show 3 other cases where it's a dash. Okay? Or not necessarily a dash, but changing the orientation of those, or the orientation of the double bonds. Okay? To make it misleading. It's not saying the only product, it's saying which is the best product of the products shown. Okay? Which is misleading because it's not stated directly in the question. So when you see stereochemistry, it's yet another reason to slow down and find the best product. They're asking you to dig really, really, really deep. And in the case of the diels-alder reaction, that is hard because there's so many steps you have to move through. Kind of, sort of? No? Yeah.
Yeah, I guess I'm just struggling a little bit with how you're using your arrows.
Yeah, because I drew the arrows wrong. No, when we set up our diels-alder reactions, almost always, where's your first arrow start at? Pi bond, which pi bond? Diene or dienophile? Diene, why should it start at the diene? There's more pi electrons. So universally you start there. Which pi bond would you typically start from? Okay. So given the correct way to draw the structure, so it's this. Which pi bond should my first arrow come from? The top one or the bottom one? Top. Why the top? Read the first word on any page. Where do you start that first word? Top. Okay, not only that, it's top, left. Another simple switch, switch the dienophile and the diene, switch the order of them. That can then confuse students as well, because it doesn't match the pattern. Okay? How ingrained are we into patterns? My green arrows make no effing sense, because I'm showing a positive charge attacking a negative charge. Why did I draw them that way? Because I'm ingrained in the pattern of saying the top double bond attacks. So much so that I actually skipped the apparently obvious charges not aligning right. So if we were to fix those arrows, how could we go through and do that? Oops. The negative attacks the positive. That comes out and attacks, which messes with all of those. This one rotates down, okay, which fixes the arrows. Okay. So if you think that patterns aren't things that we get locked into, I'm literally making the exact same mistake by locking into those patterns. Okay. We have muscle memory. It's hard to break that. Tests will test you on that muscle memory. Okay. Unfortunately. Okay? Kind of makes sense? So that's kind of our quick review in 30 minutes of the diels-alder video. Okay? Which means we're going to go back to our slides. The cyclotri electrophiles, okay, we talked about those. We have those answers from the last video. Okay. When we go through and do these, what we might find is we end up with intermediates that are unstable, okay, or structures that we don't like mercury attached to a carbon structure. We don't like that, so what has to happen? I need to add something to get rid of it, which means 2 steps. Okay. Why did I not show 2 steps? The second step isn't dealing with the electrophilic addition. It's an entirely separate chemical reaction. So what we're trying to do is address the individual types of mechanistic steps first and then deal with those secondary reactions or reagents later. In this case, it's sodium borohydride. Okay? So you may see reagents as two steps. The first step is the primary one that we're concerned about for electrophilic additions. That will then potentially be followed by something else. Right? So when we go through and look at our 4+ member transition states, okay, we need a small leaving group. Small is a really weird thing to say. Okay? This is ultimately how I looked at overall electrophilic additions. Okay? So what that's saying is that in the course of the reaction, okay, the leaving group can't leave. With our 3-membered transition states, the leaving group could leave. Why could the leaving group leave? Okay. The example, or the classic example, if we look at Br2, the electrons come up, our leaving group can leave. Why can that leaving group leave? Okay, so we can evaluate big, we could evaluate charge. All of those are going at the same topic. What are you saying is the characteristic of that leaving group? Also a characteristic, larger topic. It's stable. The leaving group is stable. Why is bromine a good leaving group? It's charged, that's bad. It's big. The very next rule on our list is size. Bromine is big. It's big enough that it can stabilize that extra charge. Okay? Because of that, it can leave, which means it doesn't fit this pattern because I need a small leaving group. Why would I need a small leaving group? Okay? It's not that I need one. It's that when I run a reaction where there is a leaving group that is small, what happens? Okay? If that leaving group is small, it can't leave. Okay? So what does it do if it can't leave? Well, if it can't leave, then the Lewis acid should never react. Okay? So what's happening is we're saying that the Lewis acid reacts with our alkene in that electrophilic addition, but now our leaving group can't leave the structure, so instead it immediately reacts back. The result being I have 1 atom, 2 atoms, 3 atoms, 4 atoms in the reaction, all arranged in a circle around each other. We have a 4-member transition state. Okay? It could be more atoms than that depending on what the quote-unquote leaving group is. The classic example is with our BH3. Okay? Boron is less electronegative than hydrogen, believe it or not, and it has an empty p orbital. That means the boron acts as, rhymes with nucleophile, an electrophile. The electrons come out, dump into the boron orbital. Now boron has exceeded its octet, so what does it do? It kicks out a leaving group. What's that leaving group? Hydrogen. Can hydrogen stabilize those electrons? No, because it's a bad leaving group, it immediately reacts back. The result being, I've now added boron and hydrogen across the double bond. Okay? Because it happened immediately, the boron and hydrogen are added to the same side of the double bond. Okay? So by understanding something about the overarching principle, I can now predict the relative orientation of the hydrogen to the boron. Okay? That's powerful because now if I'm asked something about stereochemistry, I have a way to answer that. Okay? What happens if we move to the metal center one with our osmium? Okay? This is where that whole small leaving group is like massive, huge air quotes. Okay? And any organic chemist is probably throwing stuff at me. That's fine. Okay? I don't care because it works. Shut up. Okay? If we look at our osmium structure, if you don't agree with me, that's fine. You can just memorize it. Okay? If we've got our osmium structure, okay, there's so many electronegative oxygens on that structure that the oxygens, or at least one oxygen at any given instant, is starting to lose electron density, which means that oxygen becomes positive, which makes it an electrophile. My nucleophilic pi bond can share with the oxygen. What is my leaving group on the oxygen? A pair of electrons. Is a pair of electrons a stable leaving group? No. Okay? Not stable at all. The transition doesn't quite work. The electrons go to the osmium. The osmium exceeds its octet. A pi bond from a neighboring oxygen is what shares the electrons down. The result being we end up with the 5-membered reaction. Notice what's the big difference here? This 5-membered product is an intermediate. Did I show a 4-membered intermediate with the boron? No, why not? It didn't form. The 4-membered thing was a transition state. Why can I get a 5-membered actual intermediate? What bonds am I making or am I breaking? Pi bonds, which means there's a leftover sigma. I can end up with a stable intermediate. What bonds am I breaking in the case of the boron? Sigma bonds. When I break the sigma, is there any leftover bond to keep it connected? No. That's why I don't have an intermediate. Right? So evaluating the types of bonds that are breaking can help you predict these. Right? Remember I said the hydrogen and the boron were added to the same side of the pi bond. How about these oxygens in the final product? What do you think? Should those be on the same side or opposite sides? Same side. Why can't they be on opposite sides? Okay. Where the oxygen is located physically prevents it from getting to the opposite side. I wouldn't be able to make one wedged and one dashed because it physically can't get there. Okay. Up here, they have to be added to the same side because hydrogen's not a stable leaving group and doesn't have any choice. It has to attach to the same place. I don't have any time to do any rotation because the pi bond's never actually broken until the reaction has happened. Okay? Kind of makes sense? So we end up following the same general pattern within it. Okay? What is our hybridization for BH3? sp2, right? Those of you, again, asking, well, wouldn't it take a really long time to draw out the Lewis structure? To answer that question, B, H, 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 there's 3 groups of electrons, 3 groups of electrons, okay? Means that I'm sp2 hybridized, which means there's a leftover p orbital, so that extra p orbital could do something. Yes, that takes a crap ton of time. That's why you had first semester. Okay? First semester sets up the foundation so that you can answer that by looking at the structure and immediately jumping to that answer. Okay? Once you have that, what do we do with the leftover p orbital? What's in it? Nothing. What could go in it? Electrons. Now I can address the alkene reacting with it. Okay? First semester gives you those pieces. Okay? And that doesn't mean you were an expert in first semester. I'm not making that assumption by any stretch, regardless of whether you had me or not. Okay? What we're trying to address is that that chemistry is there. We're building on it. If we choose that noise was me. Okay? I hit the wall. Okay? Sure, the chemistry was there. I honestly don't remember now. Our chemistry is there to build on. Okay? If we don't have that, how would we do second semester? You memorize. So when everybody says OChem is a ton of memorization, this is why. They don't have that fundamental building block and aren't being drawn back to that, hey, it's there, we can build from that. Okay? It's hard. It takes time and practice. Right? But once you've got it, you can build faster from it. Fun fact about that p orbital, where can we dump electrons? Above and below, which means 2 potential products. Okay? And we always have to say potential because the rest of the structure dictates the relationship between those 2 products. If they're identical products, we don't say there's 2 products. Because, well, they're identical. Okay? If they're enantiomers, well, now I have 2 products, then what's the relationship between those 2 products? Enantiomers. Okay? So I have to think about every time I go through and do an addition reaction, there potentially being 2 products. Are those 2 products different? Every single electrophilic addition. Every single addition, period. Okay? What if we had the 2Z butene. So if we go through and ran this reaction, let's say the boron reacts from the top. There's the boron, where's the hydrogen? Same side. Add more information. Also wedged. Okay. That's going to lock. Notice I'm showing those in the exact same space. Okay. Why are they being shown in the same space? Because it's a simultaneous reaction. I can't rotate that pi bond. Okay. So I'm choosing to set up my reaction or my potential products in a comfortable space where I haven't changed anything. And I'm placing those according to their reactivity. Kind of, sort of. I'm going to accept that. Okay? Of course, I picked 2E because I'm so good at nomenclature. If we actually did 2Z, meaning on the same side, okay, what happens with our product now? Again, we want to choose to maintain the orientation. I could have the boron and the hydrogen added on the same side up, or I could have the boron and the hydrogen added on the same side down. Deciding what the relationship is between those two products could very well be a multiple choice question. Okay? Kind of makes sense? How often have we seen boron attached in a structure? Not really. In fact, this is pretty much the only case. Okay, why? Do we need a second reaction? So BH3 and the mercury are both cases of this. I don't want boron connected to my carbon structure. I don't want mercury, which means I have to do something else. Okay? That something else is trying to somehow finish that off. So there are secondary reactions used to cleave the odd elements. Boron, mercury, osmium, manganese. Okay? We have to add an extra thing to get out of that. The details of those reactions are typically not necessary, which means we won't talk about them unless you specifically ask outside of class, which then means you need to memorize those end results. Okay? I apologize for that, but that's kind of where we're stuck within time. Okay? So, our workup on the mercury. When we build our mercury, we'll get the mercuronium ion. Just like the bromonium ion, mercury does not want to hold that positive charge. So a nucleophile needs to come in and help mercury out. Mercury wants more electrons. Where are the closest electrons to the mercury? Where? We would think oxygen. There's a reason why oxygen isn't drawn right next to it. There's a closer source of electrons. The sigma bonds immediately next to it. So mercury can steal those electrons. Okay, so we had a couple questions. Is what not next to what?
Isn't it drawn right next to it?
Which is closer drawn to the mercury? Mercury, sigma bonds, or mercury, you're talking about this oxygen?
Yeah.
Touche, I did not see that.
Oh, I said, is it not?
Did not see that oxygen, so let's address that real quickly. Would mercury steal those electrons from that oxygen? Why not? Oxygen, as far as we're concerned, is the most electronegative element. Okay, so that's one reason why that's bad. Okay, the other reason, what else is connected to that mercury? The positive charge is mercury. It's not connected to it. Two carbons. Okay, given the choice, carbon or oxygen, which one should mercury steal electrons from? Carbon, because it's less electronegative than the oxygen. Okay. So that addressed that. Now that we fixed up that other oxygen that I didn't see. Mo, did you have a question too?
No, I was just gonna ask what the AC is.
Okay, what is the AC? Also a good question. Okay, this group here is typically referred to as AC as an abbreviation. It actually means acetyl. If next to that acetyl I add an oxygen, it becomes acetate because it's a carboxylate. If I add a hydrogen to that oxygen, it becomes acetic acid. The root there is really acete. Okay. If it's a substituent, we get the YL. Remember, we had the YLs with our nomenclature. If I make it OH, it's now an acid, so it becomes acetic acid. Okay. If it's just an oxygen, we're aiming towards an ester. It's not an acid. We name esters as ates, so it becomes acetate. Okay. So all sorts of fun nomenclature stuff out of that, which I sort of just pulled out of my butt, but it's all right. Mercury is Hg, yes.
Why does that hydrogen equal carbon and oxygen? I know you mentioned this before.
So why would Mercury prefer to steal electrons from the carbon and not the oxygen? Carbon is less electronegative than the oxygen. So oxygen is holding the electrons tighter than carbon. Okay? Who are you going to try to steal money from? A little kid with a $5 bill or me with a $5 bill? You know me, that's not fair. A giant with a $5 bill. You're probably going to try and steal it from the kid. Why? They're weaker than the giant and probably won't smash you into the floor. Same thing's happening here. The oxygen is stronger, if you will, than the carbon, which means those electrons are spending most of their time with the oxygen, not the mercury. So that arrow, now being our red arrow, doesn't make sense given the option between red and blue.
Oh, I was thinking about that top oxygen.
We haven't even brought the top oxygen into it yet, but we can do that here in a second. Okay, so we have the AC for the acetyl. Okay, we're good there? Okay. Cool, cool, cool. Fair enough. Sometimes you'll see those abbreviations, you got to watch out for them. Never feel bad about asking, even on the exam. Okay? Does mercury want to be positive? No? What does it need? Electrons. Where's the closest source of electrons? One was to the oxygen immediately attached to it, which we decided was a bad idea. The other option? Carbon. The carbons. Okay? Which carbon? Okay. This becomes a difficult question to answer, and ultimately it all ties back to how much the atom that's in that cyclopropyl type structure, how much it wants electrons. Does mercury want to be positive? No. So it is a very good leaving group. If it is a very good leaving group, it is already leaving the structure, which means one of those carbons is now positive. Where would I rather have the positive charge? I'd rather have the positive charge on the secondary. That's the larger positive. Water comes in and attacks that position, kicks the mercury out that way. Through a sequence of other steps, because we have, first off, technically an SN2 reaction, right? Followed by, a pseudo SN1 reaction, followed by an acid base to remove the hydrogen. We'd end up with our structure as shown. We got it? Okay. The things we got to look for. How good is our leaving group? And how good is our nucleophile? We looked at the leaving group. Could we have looked at the nucleophile? Yes. Is the nucleophile good? What makes a good nucleophile? Electrons. It's what? You're right. Negative. Is it negative? No. It has electrons, so it can act as a nucleophile, but it's not a good or a strong nucleophile because it doesn't have the negative. If it's not a strong nucleophile, it's going to react with the most positive site, which means our more stable carbocation. What if it was negative? Now it's a strong nucleophile. As a strong nucleophile, what happens? We want to neutralize that strength as quickly as possible. Which carbon is more accessible? The primary. So if my nucleophile is a strong nucleophile, it attacks the primary. So the chemistry changes on you. Okay? Doesn't change with the mercury. It's always going to be with a neutral oxygen. Okay? But we will see it change with epoxides. The mercury is toxic. We need to cleave that. So what we'll do is eject it from the structure with a secondary reagent. We need hydride as a strong nucleophile to cleave the mercury. Is hydride stable? No. So how do we stabilize it? With an atom that is nice and easy to be able to stabilize extra electrons. Why would boron work as a way to stabilize extra electrons? Because of that empty p orbital. The hydride can dump its electrons in there. There's my H minus. Okay? So we end up going through the same reaction. What we're effectively looking at is very similar to our boron chemistry. Okay? The hydride dumps in, which exceeds the octet on the carbon, so it kicks electrons out to the mercury, which can react with the boron. Okay? The net result is we add hydrogen and OH across the pi bond. Okay? Notice in this case I'm not specifying any stereochemistry. How many products do we get? This is 2, top and bottom in the course of this reaction. Relationship is enantiomers. How is the OH and the hydrogen added? Syn or anti? Might be helpful if we showed that extra hydrogen, right?
You know, there are 2 products.
Come back to that in a second. Which hydrogen was added? I honestly have no idea. Because we don't know, can we specify syn or anti? No, so we don't have to worry about it. Why was there 2 products? The Y comes back to how we formed the mercuronium. Okay? It reacted with a pi bond, which means the mercury can form with the top of the pi bond or the bottom. How would we see that in our product? Because I'm pretty sure Mari didn't remember all that, or did you? No? So what did you see at this bottom that made you go there was 2 products? There's at least another answer I can think of. We don't even need to touch that. Okay. First and foremost, what did I say happens when we run an addition reaction? You get 2 products. So that could have been what you remembered. You're just like, he said, addition, 2 products. Not a bad idea. Okay. What did I add? OH and H. Can I tell which hydrogen I added? No. So is that a chiral atom? No. Is that a chiral atom? Yes. Which means the OH could be wedged or dashed. There's your 2 products. They're enantiomers. Okay. So when asking yourself, is there more than one product? Look for chiral atoms. If you find a chiral atom, almost undoubtedly yes. Okay. So our tetra intermediates, how do we remove the boron in the second reaction? This is my hand. Let's see, do I actually give the nice one? I don't. Okay. We take peroxide with hydroxide. Magic. Hydrogen. Okay. In the form of that magic, does anybody notice something interesting about this product that we did not see with our mercury product? Notice there's wedges shown through this. Why are the wedges shown? Do we know how the H and the BH or in the OH are added? Yes, you are required to know that. The H and the OH are added in a syn type addition. Okay? We might get the H in the boron, added syn. That works out really well. How do we get the OH on? That goes through a convoluted mechanism, which I'd be happy to show because I learned it, but I'm not going to show it in class. If you're interested in it, it's effectively a complicated version of how we got the H added on with the boron. It's pretty much the same thing. Okay? Ultimately, one of the oxygens of our peroxide directly replaces the boron in the exact same location. Why might that be weird? What type of reaction does it look like we did? Going from reactant to product. A substitution. What type of mechanisms do we have for substitution? SN1 and SN2. When we run an SN1, what happens to the stereocenter? What's that? We would get two products. A mixture. What is this showing? Just one. So it must be the SN2. What happens to the stereocenter in an SN2? You get inversion. Did we get inversion? No. That's why this question gets asked a lot. It's a standard substitution reaction that does not fit the mechanism of SN1 or SN2 because it's ultimately not doing an SN1 or SN2. And? Or did you guys decide not to?
Oh, no. Why are there 3 arrows there?
What each of those arrows represents is different mechanistic steps, and ultimately it's a way of saying, I'm not going to show it all, so I'm just going to show you a bunch of stuff happens. That's what it means. It's kind of a backhanded way of saying, I'm too busy to show you.
Oh.
Sorry.
No, it's fine. I just saw 2 arrows.
Yeah, it should be, it's usually 3 is how it's shown. With the last one, it was actually exactly 2. Okay. So if we went through and ran a reaction, first reaction, what do? We add OH, or is that the only thing we're adding to the structure? We're adding H and OH. So we could draw it out. I'm going to add the H and the OH.
So you're just skipping the first part of the boron, like don't care?
In this case, do I care about the product of step 1?
No, because it gets substituted with the H and the O.
Because it immediately gets replaced out. So when you look at a question, deciding should I show all the intermediates or not,
That's why you did that.
if I ask you for a mechanism, do you show all the intermediates? Yes, because mechanisms show intermediates. If I ask for the product, I don't care. Okay? And what you need to show is the final answer. Couldn't it have added OH and H? Blue versus purple? There's 2 answers I want there. Could it have done both blue and purple? Yes. Does it matter? No, because
Not in this case. 'Cause
they're the same. Those structures are identical. Okay. Could be wedged and wedged, right? Yeah, because it's a syn addition, right? Which then means, don't I also have to show OH and H? Top and bottom, right? So do I have to show both of those structures? No. Henry, why not? They're the same. Is there a tip-off with the first drawing that I drew that would allow me to say that those were the same? OH, H. Let's take a look where the hydrogen was added first. What can you tell me about that position? Is it a stereocenter? What is implied at that position? Another hydrogen. Can I tell a difference between those 2 hydrogens? Nope. So I don't care. I don't even have to show that hydrogen. Typically we don't. Okay. How about the other position where the OH is connected? Also not a stereocenter. Okay. Because of that, wedges and dashes are irrelevant. I only need one product shown. Okay. Each of those steps that we just walked through are things that you should be thinking about in split seconds. Okay. Some of that comes from memorization. Some of that comes with practice doing these questions. Okay. So it's a mix of both kind of the practice and the reiteration behind it, as well as just rote memorization. Next one, running across the left, up top, to the right. What do we end up with? What do we add? OH and H. So I could add H, and I could add OH, but I'm not going to make the same mistake that I made with the first one. That hydrogen is not a chiral atom, so that's okay. I don't need to specify that. Or I could do OH. And I'm not going to put the hydrogen on at the other location. Blue and purple, are they different? Do I get both those products? No. What reacted with the boron? The pi bond. And ultimately the electrons in the pi bond. Which of the carbons in that pi bond owns most of those electrons? The one on the end. Why? Because if I draw a resonance structure for that, I can put the positive charge on the inside versus if I drew it the other way, putting the positive charge on the outside. Which carbocation is more stable? The red bottom one. So the blue one is incorrect, which means my boron goes to that position, which ultimately means the oxygen goes to that position. The purple one is a bad structure, doesn't form. Remember how I said that resonance ability is pretty important? That helps you predict your products. Okay? If you don't have that resonance and the understanding of the chemistry there, what do you have to do? You have to memorize it. Okay? This is just like the 5th or 6th reaction that we've officially talked about. Okay? It becomes very difficult to memorize everything. Look at picking up some of the chemistry and start working on the memorization. When the memorization fails you, you have the chemistry to fall back on. Kind of makes sense? Should I draw another product? Don't I have top and bottom to worry about? There's no stereochemistry. There's 2 hydrogens at that position. I don't need to draw another product. Lower left. What do I add?
We're doing the entire mechanism for one, and we should on time. I know we've
We're-
already done it. Yeah.
Unfortunately, we're short on time, and short on time in that this is week 3, and this is all first semester still. Sorry. Okay. We need to add the H and the OH. Okay. When I look at that double bond, which carbon is more negative? The outside, which means that's where my OH needs to go. So I could draw on my OH. Okay? I would say, fooled me once and twice. I'm not going to draw the other hydrogen. What's the problem with not drawing that hydrogen? That's a stereocenter. Do I need to show the hydrogen? Yep. Extra problem on this. Not only is that a stereocenter, what is where the OH is? A stereocenter. Do I need to specify wedges and dashes on this? Yep. How do the H and the OH add? Same side. If one's wedged, so is the other one. Do I have to show the dashed ones? Technically, yes. There's 2 products. It could have attacked from the top or the bottom. There's 2 products in this one. I would technically have to show that second one, or I can get a little bit lucky because that second one is an enantiomer. So I could just write plus enantiomer. Last one. For those of you asking for mechanisms, this becomes extra irritating. Last one. If you have questions about it, by all means, you can come talk to me. Why is that our product? This is an enol tautomerization. Okay. It does the exact same chemistry up to the enol. The enol is now a new functional group that switches around, rearranges to get you the tautomer of the keto, or sorry, in this case, the aldehyde form. Okay, so we've got an enol tautomerization. That makes that one apparently more tricky, and everybody freaks out and assumes the chemistry is different. The chemistry is identical. Nothing about it changed. It's only the secondary steps that became slightly off. Yes?
For all of these, could we have more, or does it need to be hydrogen?
It has to be hydrogen peroxide and hydroxide. The hydroxide reacts with the peroxide to form the active nucleophile that initiates the reaction. So yeah, water doesn't work. Okay? Our boron products all added what? H and OH. What did the mercury product add? H and OH. What does acid in the presence of water add? H and OH. We have three reagents, all adding the same thing. Shh, no one knows on the video. Okay? 3 products all adding the same thing. Did they all add them the same way? No. Did they all add them under the same conditions? No. Okay? So depending on the rest of the structure, we may want one condition over another. Okay? That gets at the complications of each of those mechanisms. The big one for H and boron is it places the OH in the non-standard location. Okay? When we looked at the resonance structure for that lower left, we said negative charge, positive charge. Where would you expect an oxygen to be placed? The negative or the positive? You would expect it to go to the positive. Where did it go? Negative. Oh my God, that did the complete opposite of what I would expect. Anti-Markovnikov. What did the negative react with? Hydrogen. No, it didn't. Someone said hydrogen, so I followed that. Boron. Reacted with the boron. The boron was cleaved off by oxygen. The chemistry is identical for both this reaction and the mercury reaction, but you're changing the reagents. When you only look at reactants and products, then it's Markovnikov, anti-Markovnikov. If you look at the chemistry never changes. Okay? It is consistent and true all the way through. There isn't an exception. Only when you ignore the realities of chemistry and try and come up with shortcuts do you end up with exceptions. Okay? Did you want the whole mechanism? You're welcome. Now let me steal your boat. Sorry. No one? One person? Good enough. Our alkene addition summary, there's all of our reactions for our electrophilic additions. Okay? We even have some notes on here. The mercury one is nice. It generates the same result. Where'd it go? As our acid in the presence of water. But the mercury one doesn't do a rearrangement. So we even have a flag on that letting you know. If you're trying to figure out things or ways to memorize, spider diagrams are a good place to start. Which gets us into chapter 19. Oh my God, it's freaking the end of class.